Imagine a lone ember in the vast darkness of space. It glows faintly, a ghostly reminder of a fire that once raged. This ember, still incredibly hot, is no ordinary celestial body. It is a white dwarf, the remnant of a star that has lived a long and brilliant life. What becomes of these stellar remnants? Do they shine forever, or are they destined to fade away like dying embers in the cosmic night? Believe it or not, our own sun will one day become a white dwarf, a fate shared by many stars in our galaxy. Don't worry, this transformation is billions of years away, so there's no immediate cause for concern. But it's a powerful reminder that even stars, seemingly eternal, have a life cycle, just like all living things. They are born from clouds of gas and dust, they shine brightly for millions or even billions of years, and eventually, they reach the end of their fuel. When our sun exhausts its nuclear fuel, it will swell into a red giant, engulfing the inner planets, including Mercury and Venus, before eventually shedding its outer layers in a spectacular display. What remains will be a white dwarf, a dense core of matter packed into a sphere roughly the size of Earth, but with a mass comparable to that of the sun. The question that has intrigued astronomers for centuries is this: do white dwarfs last forever? They are incredibly hot, reaching temperatures of over 100,000 degrees Fahrenheit. But they no longer produce energy through nuclear fusion like our sun. Instead, they radiate their leftover heat into space, gradually cooling down over eons. This cooling process leads to a fascinating possibility: the transformation of a white dwarf into a black dwarf, a hypothetical stellar remnant so cold that it emits no detectable light or heat. Section 4. The slow fade to black. The transformation from a white dwarf to a black dwarf is, well, a slow and drawn-out process, taking billions upon billions of years. This journey is one of the most fascinating and prolonged events in the universe, showcasing the incredible timescales over which cosmic changes occur. As a white dwarf cools, its matter, primarily carbon and oxygen, becomes increasingly compressed. This compression is a gradual process where the star's core contracts under its own gravity. The atoms themselves are squeezed together, forming a bizarre state of matter known as degenerate matter. This state defies our everyday understanding of physics, existing under extreme conditions. This degenerate matter is incredibly dense. It's so dense that a single teaspoon of this material would weigh tons on Earth. Imagine squeezing the mass of the sun into an object the size of Earth. This gives you an idea of the immense density and compactness of a white dwarf. That's the density of a white dwarf. It's a stellar remnant that continues to shine, albeit faintly, for billions of years. Over unimaginable stretches of time, even this intense heat will dissipate into the coldness of space, leaving behind a dark, inert object, a black dwarf. This final stage marks the end of a star's long and fascinating life cycle. Section 5. The universe's long goodbye. The slow fade of white dwarfs into black dwarfs is a poignant reminder of the transient nature of the cosmos. These stellar remnants, once the cores of vibrant stars, gradually cool and dim over billions of years, eventually becoming